6 October 20. Scientific background on the Nobel Prize in Physics 2020. Theoretical foundation for black holes. The supermassive compact object at the Galactic Center. The Nobel Committee for Physics. Theoretical foundation for black holes and the supermassive compact object at the Galactic Center. The Royal Swedish Academy of Sciences has decided to award the Nobel Prize in Physics 2020 with one half to Roger Penrose for the discovery that black hole formation is a robust prediction of the general theory of relativity, and the other half jointly to Reinhard Genzel and Andrea Ghez for the discovery of a supermassive compact object at the center of our galaxy. Introduction. This year's Nobel Prize in Physics focuses on black holes, which are among the most enigmatic objects in the universe. The prize is awarded for establishing that black holes can form within the theory of general relativity, as well as the discovery of a supermassive compact object compatible with a black hole at the center of our galaxy. The early history. The first scientists to discuss the possibility of dark objects with an escape velocity larger than the speed of light were the English astronomer and priest John Michel in 1783 and the French polymath Pierre-Simon Laplace in works from 1796 and 1799. In a contribution to Philosophical Transactions of the Royal Society, Michel 1783, Michel calculated that a star with the same density as the Sun but a radius 500 times as large would have a gravitational pull so strong that light would be trapped and unable to escape. In his Exposition du Système du Monde, Laplace 1796, Laplace made a similar suggestion independently of Michel. He provided the full details in a mathematical treatise from 1799, Laplace 1799, where he considered a star with the same density as Earth, i.e. 4 times the density of the Sun. He arrived at a radius 250 times that of the Sun. The objects contemplated by Michel and Laplace would now be classified as supermassive black holes with masses between that of the compact object at the center of our galaxy, the subject of this year's Nobel Prize, and the black hole candidate at the center of M87, recently imaged by the Event Horizon Telescope. The calculations of Michel and Laplace were made within the framework of Newtonian mechanics. The results are easily obtained by setting the total energy of a test particle equal to 0, so that it just barely can escape from the dark object. This gives 1/2 mv squared minus gmm over r equals 0, from which it follows that a radius smaller than 2gm over c squared prevents a particle of light from reaching infinity. In his work from 1799, Laplace explicitly presented just this formula. In his work, Michel had gone even further, with an interest in the new discoveries of binary stars, speculating how one could infer the existence of these dark objects. He wrote, "We could have no information from light. If any other luminous bodies would happen to revolve around them, we might still perhaps, from the motions of these revolving bodies, infer the existence of the central ones with some degree of probability. The observations made by the teams led by Reinhard Genzel and Andrea Ghez have allowed them to make precisely this inference, for which they are awarded this year's Nobel Prize in Physics. The theoretical work by Penrose in the other half of this year's prize was essential for the study of black hole physics and a great motivation for astronomers in their search for good candidates. The Schwarzschild metric. On 13 January 1916, less than 2 months after Einstein completed his theory of general relativity on 18 November 1915, and less than 4 months before his own death, the German astronomer Karl Schwarzschild published a solution to Einstein's field equations, describing the curved spacetime around a spherically symmetric, non-rotating mass. Schwarzschild 1916. His metric takes the form ds squared equals 1 minus 2gm over c squared r times c squared dt squared minus 1 over 1 minus 2gm over c squared r dr squared minus r squared times d theta squared plus sine squared theta d phi squared. For years to come,
Only the leading term in a large radius expansion of Schwarzschild's metric was of any practical use in tests of general relativity, such as the Mercury perihelion precession, light bending, or the Pound-Repka experiment in 1960, confirming gravitational time dilation. Only recently has it become possible to test the metric beyond leading order, but it quickly became clear that the metric had two intriguing features at positions r equals 0 and r equals 2gm over c squared, where some of its components diverged or vanished. What was their significance? In the early 1920s, the French mathematician and politician Paul Painlevé 1921, and the Swedish optician Alvar Gullstrand 1921, independently found what they both believed to be a new and different solution to Einstein's equations. They each argued that their discovery rendered general relativity incomplete. In 1933, the Belgian priest and cosmologist Georges Lemaitre proved that their metric was simply a coordinate transform of the one of Schwarzschild. Lemaitre 1933. The confusion over how to interpret the metric persisted for years. Eventually, researchers determined that r equals 0 corresponds to a true singularity, while the so-called Schwarzschild singularity at r equals rs equals 2gm over c squared is just an artifact generated by the choice of coordinates. An observer can use local measurements to discern that something dramatic happens at r equals 0, but not at r equals 2gm over c squared. Only much later, through the work of David Finkelstein in 1958, the importance of different coordinate systems was fully understood. We now know that rs has an important global significance as the point of no return, which we call the event horizon. Its position precisely coincides with the value proposed long ago by Michel and Laplace, based on Newtonian gravity and the assumption of a particle nature of light. Was it just serendipity that they had found the correct expression as early as the end of the 18th century? Not completely. In special relativity, time dilation in the form of a non-trivial Lorentz factor gives rise to the relativistic expression for kinetic energy, while gravitational time dilation is associated with potential energy. To obtain the escape velocity, the energy of the test particle moving radially in the Schwarzschild background should be equated with the rest energy of the particle positioned far away from the gravitating mass. 1. Gullstrand was a longtime member of the Nobel Committee for Physics and the 1911 laureate in medicine or physiology. Ironically, he argued against awarding the prize to Einstein for taking gravitational time dilation as well as the Lorentz factor into account. The resulting equation is Ga m minus 2gmg over c squared r Gauss 1 over 2 Ga 1 minus v squared over c squared Gauss minus 1 over 2 mc squared equals mc squared, where v is the proper velocity as measured by an observer at constant radius. This has the same solution as the analogous Newtonian expression. Thus, the two calculations happen to give the same result. The period 1939 to 1964. In 1939, the American physicist Robert Oppenheimer, together with his student Hartland Snyder, managed to decipher the implications of Schwarzschild's metric. Oppenheimer and Snyder, 1939. They studied the collapse of a spherical cloud of matter and for the first time realized the full importance of the Schwarzschild radius, which they correctly identified with the presence of a horizon. The star thus tends to close itself from any communication with a distant observer. Only its gravitational field persists. A key assumption in the calculation of Oppenheimer and Snyder was spherical symmetry. Many physicists were concerned that without this assumption, the endpoint of gravitational collapse could be something entirely different. After all, if the system was not spherically symmetric, how could infalling matter focus itself to a single point and create a singularity? Could the collapse fail, with matter bouncing back out? Einstein expressed serious doubts about the existence of horizons at about the same time as the work of Oppenheimer and Snyder, Einstein 1939. Such considerations led the Soviet physicists Evgeny Lifshitz and Isaac Kalatnikov to revisit the calculations, concluding that results like those of Oppenheimer and Snyder did not represent what actually happens in a real physical situation. Lifshitz and Kalatnikov, 1963. In fact, they claimed that singularities could not occur under any realistic circumstances in general relativity. The results presented allow one to draw the important conclusion that the singularity in time is not a necessary property of cosmological models of the general theory of relativity, and that the general case of an arbitrary distribution of matter and gravitational fields does not lead to the appearance of a singularity. The American physicist John Wheeler is said to have had similar worries, speculating that quantum mechanics might hinder collapse toward a singularity, preventing the formation of this strange object called the singularity. He imagined how the collapsing star would convert itself into gravitational radiation, rapidly evaporating away, leaving nothing behind. A remarkable observational discovery would follow this theoretical development: the first observational hints for supermassive black holes. The discovery of quasar-stellar objects, abbreviated quasars or QSOs, generated a lot of interest. These were first detected as compact radio sources in all-sky surveys in the late 1950s without optical counterparts. Eventually, in the early 1960s, optical astronomers found visible blue objects associated with these sources, originally thought to be stars in our galaxy. A major breakthrough was achieved when the Dutch astronomer Martin Schmidt, 1963, following the accurate radio location obtained by Hazard, Mackey, and Schimmons 1963, identified QSO 3C273 as being an extragalactic source, with prominent spectral lines indicating a location outside of the Milky Way, at redshift Z equals 0.158. Both articles were published in the same issue of Nature in 1963. This result was very surprising, as the large distance to the point-like source, 760 MC, implied a luminosity about 1,000 times larger than that of our entire galaxy. The first discovery was soon followed by many others, at cosmological distances.
Hours, indicating a small and powerful source of energy. By 1965, Schmidt had extended the distance range of quasars to very high redshifts, Z greater than 2. Astronomers realized that quasars, rather than being isolated objects in our own galaxy, were in fact located at the center of distant galaxies, with the rest of the distant galaxy often too faint to detect. The engines behind these active galactic nuclei, or AGN, commonly produce 1039 watt, more than 2 orders of magnitude larger than the luminosity of all stars in a typical galaxy. This mind-boggling realization led to the idea that AGNs could be extremely massive stars, as heavy as several million solar masses, as first contemplated by Hoyle and Fowler 1963. However, it soon became clear that any such giant star would be extremely unstable and short-lived, and therefore could not explain the quasar observations. The singularity theorem. Schmidt's discovery prompted Wheeler to reconsider the physics of gravitational collapse, and he discussed this with Penrose, who began to think about the problem in late 1964. 2. Oppenheimer and Snyder had described the spherically symmetric case, where an astronomical body contracts to within its Schwarzschild radius, forming a singularity of infinite density. However, it was far from clear that this could happen in the real world, and whether the assumption of spherical symmetry was a prerequisite for gravitational collapse. Penrose was well aware of the rotating solution found by Kerr the year before, Kerr 1963. The solution retained a lot of symmetry and did not exclude the possibility that departures from symmetry could prevent singularities to form. Penrose set out to analyze the situation without the assumption of spherical symmetry, assuming only that the collapsing matter had a positive energy density. To do this, he had to invent new mathematical methods and make use of topology. The key concept that Penrose introduced was that of a trapped surface. A trapped surface is a closed two-dimensional surface with the property that all light rays orthogonal to the surface converge when traced toward the future. This is contrary to a spherical surface in flat space where outward-directed light rays diverge. It can be seen that in the spherically symmetric case, any spherical surface with a radius less than the Schwarzschild radius is a trapped surface, which provides a good way to understand the structure of a black hole. Examining the Schwarzschild metric, we find, as illustrated in Figure 1, that the radial direction becomes time-like as one passes through the horizon.
time and space switch roles, and the direction inwards towards the origin of spherical coordinates becomes time. Hence, it is as difficult to get back out of the black hole as it is to go backwards in time. An even more dramatic consequence of the trapped surface is that the flow of time inevitably will bring any observer towards the origin of the radial coordinate, where time ends. All the matter that formed the black hole resides at this single moment in time, the singularity.
Figure 1. Schematic diagram showing the interior of a black hole. Inside of the horizon, the radial direction is time-like. Time ends at the singularity. Such trapped surfaces can also be found in the case of rotating black holes. In fact, the trapped surface remains regardless of how the solution is perturbed, and its existence is independent of any assumptions about symmetry. After realizing the power of the idea of trapped surfaces, Penrose proceeded to prove that once a trapped surface had formed, it is impossible, within the theory of general relativity and with a positive energy density, to prevent the collapse towards a singularity. Penrose, 1965. See Figure 2. Figure 2. The diagram is based on Penrose's paper from 1965 and shows the collapse of matter into a black hole. On a trapped surface, all light cones are tipped inwards, and the formation of a singularity is inevitable. To visualize space-time, Penrose introduced a technique using conformal transformations, Penrose 1963. Such transformations can change the scale, but they always retain angles. This means that points infinitely far away in space and events in the infinite past or future can be brought in from infinity to fit inside a diagram of finite size. If a light ray originally corresponds to a line at 45 degrees, it will remain at the same angle after the conformal transformation. Such diagrams are called Penrose diagrams, and they are indispensable tools in the study of curved spacetimes. A Penrose diagram where a star collapses to form a black hole is shown in Figure 3.
Figure 3. A Penrose diagram of a star that collapses into a black hole. Time runs upwards, and light rays are inclined at 45 degrees. Penrose's result is heralded as the first post-Einsteinian result in general relativity. It proves that gravitational collapse cannot be stopped after the trapped surface is formed. One should note that its formation happens at a stage in the collapse when density of matter is not very high. The supermassive black holes of Michel and Laplace have average densities no higher than those of the Sun or Earth. A few years later, Penrose, together with Stephen Hawking, went further to show that similar results also apply to cosmological singularities. Hawking 1965, Hawking and Penrose 1970. Under reasonable assumptions, a past singularity is inevitable in the Big Bang model. Penrose 1969 wrote a beautiful summary of many of these results. In a review article, Senovilla and Garfinkel 2015 provide a thorough description of the theorem and its historical background. Penrose's discovery triggered a new era in physics and astronomy. The strange dark objects that Michel and Laplace speculated about were deeply rooted in our modern picture of gravity. It was after Penrose's discoveries that black hole finally stuck as the name for this exotic gravitational anomaly. The American physicist Robert Dicke was the first to use the term during lectures at Princeton in 1960, and Wheeler later helped make it popular. Herdero 2018. Supermassive black holes become the leading model to explain quasars. After the discovery of the extragalactic nature of 3C273, emission of radiation from accretion of matter onto supermassive black holes became the generally accepted explanation for quasars. Salpeter 1964, Zeldovich and Novikov 1965. This was a plausible extension to the models for X-ray and radio emission from matter falling into much lighter stellar mass black hole candidates, such as the ones observed by the group led by Riccardo Giacconi, the 2002 Nobel laureate. The gravitational pull must come from an extremely massive object, or else they would exceed the Eddington limiting luminosity. LL equals 4 pi AFC mic MPC, sigma T equals approximately 1.3 times 10 to 31 watts times m times the sun over m times the sun, where MP is the proton mass, m times the sun, the mass of the sun, and sigma T the Thomson cross-section. at which point the radiation pressure would overcome gravity, rendering instabilities, which would blow the object apart. Since the luminosity of 3C273 is at least 10 to 40 watts, the enclosed mass must exceed 1.9 times 10 to 9 m times the Sun for the source to achieve equilibrium. A refined theoretical description of the phenomenon was presented by Donald Lynden Bell, 1969, who also suggested that many, if not most galaxies, host a heavy black hole at their center. He asserted that such a supermassive black hole with a mass as large as 10 to 6 to m to n, a spiral at their center, would be infatuation to what the Milky Way holds. Exception, and in a very influential paper, 2 years later, Lynden Bell and Martin Rees, Lynden Bell and Rees, 1971, argued for the existence of a supermassive black hole in the galactic center and proposed key observations to explore the nature of the compact object. Earlier, Kerr, 1963, had generalized the Schwarzschild solution to describe a rotating black hole, adding angular momentum to mass and electric charge, Newman et al., 1965, as the principal physical parameters describing black holes, irrespective of how they were formed. A critical observable is the innermost stable circular orbit, ISCO, which is at a distance 3 rs from a Schwarzschild non-rotating black hole. Matter closer than that will therefore fall directly into the black hole, adding to its mass. Furthermore, as matter spirals into its final destiny, up to between 6% and 42% of its rest mass energy can be released, depending on the rotational energy and the black hole's spin direction with respect to the spiraling infalling matter. This supermassive black hole hypothesis thus provided a plausible explanation for the high luminosity of quasars. In 1969, Penrose realized that the rotational energy of a Kerr black hole could be another important source of energy, further elaborating this realization 2 years later, Penrose and Ford, 1971. The mechanism by which this energy is released is far from trivial. In classical mechanics, there are a few ways to obtain energy from a rotating body. Projectiles can be shot so that they bounce off the surface, increasing their speed while the rotation of the body decreases. Tidal forces transfer the rotational energy of the Earth to the orbital energy of the Moon. A black hole has no hard surface, so how can the energy transfer occur? Outside of any rotating object, including the Earth, space-time is dragged along with the rotation, giving rise to the Lentz-Thirring effect. The effect is small for Earth, but close to a rotating black hole, the effect is dramatic. Just outside of the horizon, there is an ergosphere, within which it is impossible for an observer to resist the rotation of space-time. If the black hole is rotating, say, in a clockwise direction, the observer will be carried around in a clockwise direction, even if the observer is trying hard to move in the opposite direction. Penrose found that it is possible to make use of the ergosphere to extract energy. He envisioned how a projectile sent inside of the ergosphere splits into two, with one piece entering through the horizon and the other leaving the ergosphere and escaping from the black hole. Penrose showed that this process can happen in such a way that the escaping piece has a total energy that is larger than the energy of the original projectile, with the extra energy extracted from the rotating black hole. This process seems contrary to the conventional wisdom that nothing can get out of a black hole and that a black hole can only grow in size. The solution to the apparent paradox lies in how to define the size of a black hole. As understood by Stephen Hawking, 1972, it is the area of the horizon of a black hole that never can decrease in size. A Schwarzschild black hole has mass in direct proportion to its area. If the area cannot decrease, neither can the mass. The case of a rotating black hole is more complicated. The Kerr metric leads to A equals 8 pi m times m plus times root m squared minus a squared, where the parameter A measures the angular momentum of the black hole. Remarkably, the mass can decrease even if the area grows, thus making the Penrose process possible. Following work of Jacob Bekenstein, 1972, Hawking went on to study the remarkable connection between black hole physics and thermodynamics, with area acting as entropy, Hawking 1975. He discovered that as a consequence of quantum mechanics, black holes have a tiny temperature and are expected to emit radiation. Even though the radiation is far too weak to be measured in the case of astrophysical black holes, The discovery of this process has been of fundamental importance for the development of quantum gravity. In 1977, Roger Blandford and Roman Snijek used Penrose insight to construct a realistic model of how the rotation of a black hole could be used to generate power. Blandford and Snijek, 1977. If magnetic fields are present, these will be carried along with the ergosphere. In this way, the rotating black hole can act as a gigantic electric dynamo. This process is considered to play an important role for many black holes and their jets. Early tests of the hypothesis of supermassive black holes in galactic nuclei. The angular resolution of telescopes in the early 1990s was insufficient to spatially resolve objects separated by distances comparable to the size of the Schwarzschild radius of a possible supermassive black hole at the center of our galaxy, or even much heavier supermassive black holes in other galaxies. However, observations of the orbits of stars and gas can help determine the gravitational potential due to objects at the center of the galaxy. One can then infer whether a single compact source or dense cluster of known stellar objects, e.g., neutron stars, white dwarfs, or even low-mass black holes, could account for the observations. Black hole mean densities, computed as the ratio of their mass to the volume enclosed within a radius of 3 rs, the ISCO, scale inversely with the square of their mass. Rho equals C6 over 288 pi G3 M2. For a supermassive black hole weighing 4 times 10^6 m², the density is actually only about 40 times larger than that of water. However, when converted to astronomical scales, this amounts to 6 times 10^23 m² Pc-3, 1 Pc equals 3.26 light-years, much larger than the density of any known stellar cluster. Globular clusters with a density of 10^5 m² ppc-3 are the densest known long-lived multi-body systems in our galaxy. Thus, the general observational strategy to identify the existence of supermassive black holes was based on the determination of mass density within the innermost region of galaxies, then comparing this density with known stellar clusters. An additional strategy based on direct imaging would come much later with the observations of the Event Horizon Telescope reported in 2019. The study of AGNs became much more accessible with the launch of the Hubble Space Telescope, HST, and its unprecedented angular resolution at optical wavelengths. About 50 nearby AGNs were targeted for observation. Multi-wavelength observations of a powerful jet originating at the nucleus of the nearby elliptical galaxy M87 in the Virgo cluster were particularly interesting. Early HST observations, Ford et al. 1994, Harms et al. 1994, indicated the presence of a rotating disk in M87 with mass of a few times 10^9 m² confined within 18 pc from the nucleus. This result was derived from the kinematics of the gas in the disk, and the angular scale probed in this case corresponded to about 3 times 10^4 rs. While very suggestive of a central supermassive black hole, the observations could not rule out the possibility that the gravitational potential was due to a dense cluster of stars too faint for detection. The first empirical claim that a dense stellar population could not account for the kinematic motion around a galactic center was made by Miyoshi et al. 1995. They made observations of a rotating H2O maser disk at 0.13 pc from the center of one of the closest active AGNs, the nucleus of the galaxy NG4258, at a distance of 7.3 mparsec. Observations made at the 1.3 centimeter radio wavelength Very Long Baseline Array VLBA showed a thin disk containing H2O masers surrounding the mildly active nucleus. Exploiting the power of the Very Long Baseline Interferometry technique, they mapped the location and velocity of the masers with an angular resolution better than a milliarcsecond. The rotation curves follow Keplerian orbits around compact central source with a mass of 3.7 times 10^7 m², corresponding to a density in excess of a few times 10^9 m² ppc-3. This density is inconsistent with the long-lived dense cluster of stellar mass astrophysical sources. The center of the Milky Way as a laboratory for fundamental physics. The central few parsecs of the Milky Way harbors a rich cluster of stars and hot gas. These have been used to trace the gravitational potential of the galactic center, defined by the compact radio source Sagittarius A star, at a distance of 25,000 light-years. If the mass concentration at
the stars at a distance r from the center should be proportional to 1/r1/2, i.e., growing for progressively smaller radii, as for planets around the Sun. Such Keplerian orbits should not arise if the mass is due to a spatially extended cluster of stellar mass objects. With spatially distributed mass, the velocities would increase with distance or be less independent of distance, depending on the density profile of the stellar cluster. Thus, observations of stellar velocities became essential to the exploration of a possible supermassive black hole in the galactic center. Focused observational programs led by Ghez and Genzel. Two observational teams, one led by Genzel at the Max Planck Institute for Extraterrestrial Physics, MPE, and the other by Ghez at the University of California, Los Angeles, have been monitoring the motions of stars orbiting the galactic center for nearly 3 decades. Genzel's group used telescopes in Chile, operated by the European Southern Observatory, ESO, while Ghez and her colleagues used the Keck Observatory in Hawaii. Distinguishing individual stars in orbit in the very crowded region at the galactic center requires excellent spatial resolution. Obscuration by interstellar dust in the center of the Milky Way inhibits observation at optical wavelengths, with less than about 1 photon per billion penetrating the dust along the line of sight to Earth. Therefore, the two teams carried out their observations in the near-infrared, the astronomical K-band, centered at lambda equals 2.2 mu. At these longer wavelengths, the mean free path of photons is much larger, reducing the attenuation to only about a factor of 10, thus making the observations feasible. The long measurement time needed to recover the signal and follow the stellar orbits around the galactic center rendered space-based observations impractical. Ground-based observations were necessary, and the challenge became finding ways to compensate for the blurring that results from changes in Earth's atmosphere during the long measurement time. The technical solutions developed by both teams were key to their successes. Detection of stellar motions in the galactic center. Turbulence in the Earth's atmosphere smears the photon trajectories at timescales shorter than about 1 second. To compensate for this, both teams initially developed and used the technique of speckle imaging in the near-infrared. Very short exposures, just above 1/10 of a second, were acquired with a very sensitive detector. The series of short exposures were spatially shifted to align the pattern of stars and added. The stack of shifted images provided a sharper and deeper image, ultimately limited by diffraction. For K-band observations at the 10-meter telescope, the diffraction limit is about 0.05 arcseconds, corresponding to a spatial scale of 2.5 light days at the galactic center. Figure 4 from Ghez et al. 1998 compares an individual image of the galactic center with those resolved from speckle imaging at the Keck telescope. The power of the technique to spatially resolve the stars in the central parsec region surrounding SGR star is clear. With high angular resolution, the resulting projected velocity vectors of a handful of stars could be determined after a survey over 4 years on the 3.5-meter New Technology Telescope, NTT, Eckhart and Genzel 1996-1997. Genzel's team could also reach the diffraction limit on spatial resolution with the specially constructed SHARP camera. The velocity v of the stars, inferred from the shifts in their positions resolved through diffraction-limited images, led to a successful measurement of the v proportional r-1/2 behavior expected for a single massive point source, as shown in Figure 6.
Figure 4. A. One of the many short TECs exposures of the stellar cluster surrounding the galactic center using the Keck I 10-meter telescope, showing the speckle pattern dominated by one bright speckle. B. The individual frames are shifted to the same location using a bright reference source. C. The resulting positions of the stars are shown. D. The diffraction-limited central 1x stellar region surrounding the compact object. From Ghez et al., 1998. Figure 5. Proper motions and vectors of selected stars surrounding the central compact radio source SGR star, marked with a cross. The measurements were carried out over 4 years, and the offsets were determined with respect to the base epoch in 1994, from Eckhart and Genzel. Figure 6. Projected stellar velocity dispersion as a function of projected distance from SGRA from a set of measurements, culminating with the innermost points within 0.2 parsec, circles, obtained from measurements with the sharp camera on the ESO 3.5 meter NTT. The curves indicate the expectations from a supermassive black hole with 2.5 million solar masses. Adding more recent data from VLT and Keck, the mass estimate increased to over 4 million, from Eckhart and Genzel, 1997. The era of adaptive optics, tracing individual star orbits. The short exposure times involved in speckle imaging limited the monitoring to only the brightest stars, and lengthy surveys were required to extract a robust determination of the projected velocity. These limitations were overcome when adaptive optics, first envisioned by Babcock 1953, became available to Gez's team at the Keck Observatory, Wisniewicz et al. 2000, and Genzel's team at the Very Large Telescope, VLT, operated by ESO, Rousset et al. 2003. As shown in Figure 7, the adaptive optics technique uses a bright reference object next to the observation target, either a bright star or even an artificial star created by laser excitation of sodium atoms in the upper atmosphere. A deformable secondary mirror changes shape to compensate for aberrations to the known reference object. The compensation is performed in real time with a feedback loop, thus enabling long exposure time and the creation of much sharper and deeper images, down to the diffraction limit. This technological revolution also allowed for the use of a spectroscopy to study the stars, adding 2 important features. The composition of the stars could be studied, and, crucial to the project, radial velocities could be measured in addition to the projected velocities. At ESO, Genzel's group started a program at the 8-meter VLT using adaptive optics imaging with the NACO instrument and spectroscopy with Symphony. Not only statistical measurements of the stellar motions were made with the new technique, but most importantly, individual stars could be accurately monitored in a manageable timescale. Figure 7. The principle of adaptive optics. A laser system is used to make artificial guide stars that sense the blurring in the Earth's atmosphere. The images of the bright spots generated by the laser, 1, are used in a feedback loop to introduce fast deformations of a secondary mirror, 2, that effectively correct for the atmospheric turbulence in the science images, 3. The discovery of a compact object in the galactic center. One of the stars labeled as S2 by Genzel's group, called S02 by the team led by Ghez, was shown to have a very short orbiting period around SGR-A star, just under 16 years. Schoedel et al. 2002, Ghez et al. 2003. For comparison, it takes over 200 million years for the Sun to complete a full orbit around the galactic center. This star has a highly elliptical orbit with eccentricity E equals 0.88. Its pericenter distance from SGR-A star in the spring of 2002 was a mere 17 light hours, or 1,400 RRS. For a black hole of mass 4 × 10⁶ MO, see Figure 8. The plane of the orbit has an inclination of about 46 degrees with respect to the plane of the sky. The agreement between the data from the NTT/VLT and Keck telescopes was excellent. The analysis of the combined datasets showed that the extended mass component, visible stars, stellar remnants, and possibly dark matter, within the orbit of S2, gave a negligible contribution to the estimation of the central mass. Ghez et al. 2008, Gillison et al. 2009, b. The work of the two teams together established that the galactic center contains a highly concentrated mass of some 4 million solar masses within the pericenter, i.e. within 125 AU. This requires a minimum density of 5 × 10 to the 15 MOPPC3. The mass centroid lies within +2 milliarcseconds of the position of the compact radio source SGR-A star, which itself has an apparent size of less than 1 AU. Shen et al. 2005, Bauer et al. 2006, Doleman et al. 2008, and lacks detectable proper motion, Reed and Brunthaler 2004. A robust interpretation of these observations is that the compact object at the galactic center is compatible with being a supermassive black hole. Further support for this conclusion comes from the fact that near-infrared and X-ray flares are observed from the same position, which can be naturally ascribed to variations in the accretion flow towards a massive black hole.
Figure 8. Orbit of the star S2, on the sky, left panel, and in radial velocity, right panel. Data from NTT/VLT and Keck are shown. Blue filled circles denote the NTT/VLT points, and open and filled red circles are the Keck data. The positions are relative to the radial position of SGR-A star, black circle. The gray crosses are the positions of various SGR-A star infrared flares. From Genzel, Eisenhower, and Ghez, 2010. Recent updates on galactic center results. The ESO/VLT observations using interferometric imaging and astrometry connecting the 4 VLT telescopes have now been carried out by the Gravity Collaboration, Abuter et al., 2018, with Genzel among the leading investigators. Gravity has achieved an angular resolution of only 20 microarcseconds, about 100 times sharper than the first sharp speckle imaging results. Figure 9 summarizes 26 years of imaging the motion of the S2 star around SGR-A star, based on observations with ESO telescopes. The upper right panel shows the spectroscopic observations from both Keck and ESO that were used to measure the radial velocity. The observations are now precise enough that the position of the star can be seen to change between consecutive nights, as indicated in the bottom right panel. The best fit of the orbit, including special and general relativistic effects, is shown as a solid line in the plots. Not only have the measurements provided exquisite kinematic evidence for a compact object in the galactic center, but also a sub% error estimate of the distance to the galactic center, and a 20 sigma detection of the relativistic corrections needed to model the orbit of the star to the supermassive black hole. Furthermore, the team was able to detect the relativistic precession of the orbit, a truly remarkable experimental achievement addressing fundamental physics. Figure 9, summary of the observational results of monitoring the S2 SGR-A star orbit from 1992 to 2018. Left, projected orbit of the star S2 on the sky J2000 relative to the position of the compact radio source SGR-A star, brown crossed square at the origin. Triangles and circles and 1 sigma uncertainties denote the position measurements with sharp at the NTT and NACO at the VLT, color-coded for time, color bar on the right side. The cyan curve shows the best-fitting S2 orbit to all these data, including the effects of general and special relativity. The bottom right panel shows a zoom-in around pericenter in 2018. Upper right, radial velocity of S2 as a function of time, squares, Sinfoni NACO at the VLT, triangles, NIRC2 at Keck. S2 reached pericenter of its orbit at the end of April 2000 and then again on 19 May 2018. The cyan curve shows the best-fitting S2 orbit to all these data, including the effects of general and special relativity. From Abuter et al. 2018. Detection of motion of heated matter near the innermost stable orbit. The data do not yet allow scrutiny of the compact object closer than several hundred Schwarzschild radii, as shown by the orbit of the S2 star in Figure 9.
That could change in the future as deeper observations may reveal stars closer to SGR-A star. However, short infrared flares, about 1 hour in duration, have been serendipitously discovered over several years. Genzel et al. 2003, Ghez et al. 2003. These flares originate from the immediate vicinity of the compact object, and the improved angular resolution of gravity potentially allows the use of the flares to trace the innermost regions surrounding SGR-A star. Abuter et al. 2018. The sources of the flares appear to orbit around the central object with 30% of the speed of light at a physical distance of only 3 to 5 RRS, corresponding to the region just outside the innermost stable circular orbit of a Schwarzschild-Kerr black hole of 4 million solar masses. These observations provide additional strong support for the hypothesis that the compact object at the galactic center is a supermassive black hole, as predicted by the theory of general relativity.
Summary. Penrose's discovery of a singularity theorem showed that black holes are a robust consequence of the theory of general relativity, forming naturally in very overdense regions. During the more than half a century that has passed since this conceptual breakthrough, technological advances have enabled probing closer and closer to the black hole event horizon. The observations by LIGO rewarded the Nobel Prize in 2017, and the exquisite observations by Genzel and Ghez sharing this year's prize, as well as the remarkable picture of the center of M87 taken by the Event Horizon Telescope, are all compatible with the existence of supermassive black holes. The extent to which the structure of a black hole surrounded by an event horizon actually match the predictions of general relativity is still an open question. Nature may still have surprises in store. References. Abuter, R. et al., Gravity Collaboration, 2018, Detection of the gravitational redshift in the orbit of the star S2 near the galactic center massive black hole, Astronomy and Astrophysics, Volume 615, DOI 10.1015/0043-1678/2018-33718. Babcock, H.W., 1953, The Possibility of Compensating Astronomical Seeing, Publications of the Astronomical Society of the Pacific, Volume 65, Number 386, p. 229, DOI 10.1016/126606. Bekenstein, J. 1972, Black Holes and the Second Law, Nuevo Cemento Letters, Volume 4, p. 99-104. Blandford, R.D., and Znajek, R.L., 1977, Electromagnetic Extraction of Energy from Kerr Black Holes, Monthly Notices of the Royal Astronomical Society, Volume 179, p. 433-456, DOI 10.1016/126606. Bauer, G.C., Goss, W.M., Falke, H., Backer, D.C., and Lithwick, Y., 2006, The Intrinsic Size of Sagittarius A Star from 0.35 to 6 centimeters, The Astrophysical Journal, Volume 648, Number 2, page L127 to L130, DOI 10.1016/126606. Doloman, S.S., Weintraut, J., Rogers, A.E.E., Plambeck, R., Fronder, R., Tillanis, R.P.J., Freeberg, P. et al., 2008. Event Horizon Scale Structure in the Supermassive Black Hole Candidate at the Galactic Center, Nature, Volume 455, Number 709, page 78-80, DOI 10.1016/126606. Eckhart, A., and Genzel, R., 1996. Observations of Stellar Proper Motions near the Galactic Center, Nature, Volume 383, Number 6599, page 415-417, DOI 10.1016/126606.
Eckhart, A., and Genzel, R., 1997, Stellar Proper Motions in the Center 0.1 pc of the Galaxy, Monthly Notices of the Royal Astronomical Society, Volume 284, Number 3, page 566 to 598, DOI 10.1016/126606. Einstein, A., 1939, on a stationary system with spherical symmetry consisting of many gravitating masses, Annals of Mathematics, Volume 40, Number 4, page 922 to 936. Finkelstein, D., 1958, Past-Future Asymmetry of the Gravitational Field of a Point Particle, Physical Review, Volume 110, Number 4, page 965 to 967, DOI 10.1016/126606. Ford, H. C. Harms, Z. Twistanovan, G. Hardig, J.F. Dressel, L. Lithwick, R.C. Balin, R.C. Deffer, G.A. Boter, E.T. et al., 1994, Narrowband HST images of M87, evidence for a disk of ionized gas around a Garfinkel, D. and Senevilla, J.M.M., 2015, the 1965 Penrose singularity theorem, Classical Quantum Gravity, Volume 32, Number 12, pp. 124008. Also available as Archive 1410.5226. Genzel, R. Schodel, Ott, Eckhart, A. Alexander, Lacombe, F. Rouen, et al., 2003, near-infrared flares from accreting gas around the supermassive black hole at the galactic center, Nature, Volume 425, Number 6961, pp. 934 to 937, DOI 10.1038/Nature02065. Genzel, R., Eisenhower, F., and Gillison, S., 2010, The Galactic Center Massive Black Hole and Nuclear Star Cluster, Reviews of Modern Physics, Volume 82, Number 4, pp. 3121 to 3195, DOI 10.1103/RevModPhys.82.3121. Ghez, A.M., Klein, B., L., Morris, M., and Becklin, E., 1998, High Proper Motion Stars in the Vicinity of Sagittarius A star, Evidence for a Supermassive Black Hole at the Center of Our Galaxy. The Astrophysical Journal, Volume 509, Number 2, pp. 678 to 686, DOI 10.1036/306528. Ghez, A.M., Duchenne, G., Matthews, K., Hornstein, S.D., Tanner, A., Larkin, J., Morris, et al., 2003, the first measurement of spectral lines in a short-period star bound to the galaxy's central black hole, a paradox of youth. The Astrophysical Journal, Volume 586, Number 2, pp. L127 to L131, DOI 10.106/3748804. Ghez, A.M., Salim, N., Nielberg, N., Liu, J., R., Doe, T., Dunn, J., Matthews, K., et al., 2008, Measuring Distance and Properties of the Milky Way Central Supermassive Black Hole with Stellar Orbits. The Astrophysical Journal, Volume 689, Number 2, pp. 1044 to 1062, DOI 10.1068/592738. Gillison, S., Eisenhower, F., Trippe, A., Alexander, Genzel, R., Martins, F., and Ott, T., 2009a, Monitoring Stellar Orbits Around the Massive Black Hole in the Galactic Center, The Astrophysical Journal, Volume 692, Number 2, pp. 1075 to 1009, DOI 10.1088/637x/692/2/1075. Gillison, S., Eisenhower, F., Fritz, T.K., Bartko, H., Dodds Eden, K., Poole, O., Ott, T et al. 2009b. The orbit of the star S2 around SGRA star from Very Large Telescope and Keck data. The Astrophysical Journal, Volume 707, Number 2, pp. L114 to L117, DOE 10.108-00430-637X/707/2/L114. Gullstrand, A. 1921, Allgemeine Lösung des statischen Einkörperproblemens in der Einsteinschen Gravitationstheorie, Archiv für Mathematik, Astronomie und Physik, Volume 16, Number 8, pp. 1-15. Harms, R. J. et al. 1994, HST-FOS spectroscopy of M87, evidence for a disk of ionized gas around a massive black hole, the Astrophysical Journal, Volume 435, PL35, DOE 10.1086/18758. Hazard, C., Mackey, M., B., and Shimmons, A. J., 1963. Investigation of the radio source 3C273 by the method of lunar occultations. Nature, Volume 197, Number 4872, pp. 1037-1039, DOE 10.1038/1971037A0. Hawking, S.W., 1965, Occurrence of Singularities in Open Universes, Physical Review Letters, Volume 15, Number 17, pp. 689-690, DOE 10.1103/PRPhys.15.689. Hawking, S.W., and Penrose, R. 1970, The Singularities of Gravitational Collapse and Cosmology, Proceedings of the Royal Society of London, Series A, Volume 13, Number 1519, pp. 529-548, DOE 10.108R/RSPA.1970.0021. Hawking, S.W., 1972, Black Holes in General Relativity, Communications in Mathematical Physics, Volume 25, pp. 15. Hawking, S.W., 1975, Particle Creation by Black Holes, Communications in Mathematical Physics, Volume 43, Number 3, pp. 199-220, DOE 10.1070/BF00345020.
Herdeiro, CAR, and Lemos, JPS, 2018. The Black Hole, 50 Years After, Genesis of the Name. Gazeta de Física, 41-2. Archive, 18-11-0658. Kerr, R.P., 1963. Gravitational Field of a Spinning Mass as an Example of Algebraically Special Matrix. Physical Review Letters, Vol 11, número 5, pp. 237-238, DOI 10.1103/Physic Review Let 11.237. Laplace, P.S. 1799. Beweis des Satzes, dass die anziehende Kraft bei einem Weltkörper so groß sein könne, dass das Licht davon nicht ausströmen kann. Allgemeine geografische Epimeridenen, Vol 4.16. Laplace, P.S. 1796. Exposição do Sistema do Monde, Parte 2. Lemaitre, G. 1933. L'univers en expansion. Analyse de la Société Scientifique de Bruxelles. Vol A53. pp. 51-85. Lifshitz, E.M. e Kalatnikov, I.M. 1963. Investigations in Relativistic Cosmology. Advances in Physics. Vol 12, número 46. pp. 185-249, DOI 10.1873/1963. Lynden-Bell, D. 1969,
Galactic nuclei as collapsed old quasars. Nature, vol 223, número 5077, pp. 690-694. DOI 10.1803/223-690A. Lyndon Bell, D. e Rees, MJ, 1971. On Quasars, Dust and the Galactic Center. Monthly Notices of the Royal Astronomical Society, Vol 152, p. 461, DOI 10.193A/152.4.461. Michel, J. 1783. On the means of discovering the distance, magnitude, etc. of the fixed stars in consequence of the diminution of the velocity of their light, in case such a diminution should be found to take place in any of them, and such other data should be procured from observations as would be farther necessary for that purpose. Philosophical Transactions of the Royal Society of London, Vol 74, pp. 3557. Miyoshi, M. Moran, J. Herrnstein, L. Greenhell, N. Nakai, P. Diamant, and Inoue, M. 1995. Evidence for a black hole from high rotation velocities in a subparsec region NGC 4258. Nature, vol 373, número 6010, pp. 127-129. DOI 10.1803/37127A. Newman, E. T. et al., 1965. Metric of a Rotating Charged Mass, JMathP, 6 pp. 918-919. DOI 10.1903/1.704351. Oppenheimer, J.R., Snyder, H. 1939. On Continued Gravitational Contraction, Physical Review, Vol 56, número 5, pp. 455-459. DOI 10.1903/physicreview.55.4. Painevert, P. 1921. La Mécanique Classique et la Théorie de la Relativité. Comptes-rendus, Académie des Sciences, série não especificada, Vol 173, pp. 677-680. Penrose, R. 1963. Asymptotic Properties of Fields and Spacetimes. Physical Review Letters, Vol 10, número 2, pp. 6668. DOI 10.1903/Physics Review Let 10.66. Penrose, R. 1965. Gravitational Collapse and Spacetime Singularities. Physical Review Letters, Vol 14.3, pp. 5759, 1965. DOI 10.1903/physicreview.14. Penrose, R. 1969. Gravitational Collapse, The Role of General Relativity, no Ovo Condimento Revista, série P. 252. Penrose, R. e Floyd, F. M. 1971. Extraction of Rotational Energy from a Black Hole. Nature Physical Science, Vol 229, número 6, p. 177-179A. DOI 10.1830, PACRE 229-177A0. Penrose, R. 1989. In Penrose, New Mind, Oxford University Press. Penrose, R. 2010. Cycles of Time, An Extraordinary View of the Universe, The Bodley Head, S. 886 pontos.
Reed, M.J., and Brunthaler, 2004. The Proper Motion of Sagittarius A Star, 2. The Mass of Sagittarius A Star. The Astrophysical Journal, Volume 616, Number 2, pages 872 to 884. DOI 101.86/424960. Rossett, G. et al., 2003. NAOS, the first AO system of the VLT, on sky performance, in Adaptive Optical System Technologies, 2, Volume 4839,
pages 140 to 149, DOI 101.17/12.459332. Salpeter, E.E., 1964, Accretion of Interstellar Matter by Massive Objects, The Astrophysical Journal, Volume 140, pages 796 to 800, DOI 101.46/147973. Senovilla, J.M.M., and Garfinkel, 2015, The 1965 Penrose Singularity Theorem, Classical and Quantum Gravity, Volume 32, Number 12, DOI 101.08/0264/32/12/124008. Schmidt, M., 1963, 3C273, A Star-like Object with Large Redshift, Nature, Volume 197, Number 4872, page 1040, DOI 101.08/1971040 A0. Schwarzschild, K., 1916, Über das Gravitationsfeld eines Massenpunktes nach der Einsteinschen Theorie, Sitzungsberichte der Königlich Preußischen Akademie der Wissenschaften, 1916. Schodel, Ott, T., Genzel, R., Hoffman, R., Leonard, R., Eckart, N., Muawad, et al., 2002, A star in a 15.2-year orbit around the supermassive black hole at the center of the Milky Way, Nature, Volume 419, Number 608, pages 694 to 696, DOI 101.03/Nature 0112. Shen, Z-Q, Lo, K.Y., Liang, M, C, Ho, P.T.P., and Zhao, J.H., J., 2005, a size of circa 1 AU for the radio source SGR, A star, at the center of the Milky Way. Nature, Volume 438, Number 706, pages 62 to 64, DOI 101.03/Nature 04205. Wisenowicz, P., et al., 2000, First Light Adaptive Optics Images from the Keck 2 Telescope, A New Era of High Angular Resolution Imagery, Publications of the Astronomical Society of the Pacific, Volume 112, Number 769, pages 315 to 319, DOI 101.06/31654. Zeldovich, Y.B., and Novikov, I.D., 1965, Mass of Quasi-Stellar Objects, Soviet Physics Stockly, Volume 9, page 834.